Okay, hello everyone. Welcome to 130B, Quantum Mechanics. Let's maybe start our lecture today. So today we will continue our discussion of quantum dynamics, which is about time evolution of quantum state. Last time we have learned about unitary operators, which turns out to be very important in understanding the time evolution of a quantum state. As an introduction or motivation, we start with this discussion of basis transformation, because unitary operator can always be viewed as an operator that performs basis transformation. So what is basis transformation? It means if you have two sets of orthonormal bases, you want to change the representation from one basis to another basis, either for the state vector or for the quantum operators. What you need to do is to do a linear transformation of these either vector components or matrix components, and the linear transformation is actually described by a unitary matrix whose ith row and jth column matrix element is given by the scalar product between the two bases. So at a higher level, if you write it as an operator form, it basically corresponds to an operator which takes you from one basis to another basis. This I labels the ith basis state. This prime means it's in one basis and no prime in the other basis. So this operator simply takes every eigenstate or basis state to a new set of basis states, and by doing that, you effectively performs the basis transformation. So these are a closer look of unitary operators, but in general, at a very high level, unitary operator is just defined by this defining property, which is this equation, where dagger means the Hermitian conjugate. So U dagger U and U dagger equals 1 basically means any operator whose Hermitian conjugate is on inverse, then this operator is said to be unitary. Another way of saying that every unitary operator meets its Hermitian conjugates, they multiply together, they will cancel each other, they will vanish and becomes an identity operator. And that's a key mathematical property of unitary operator that defines what we mean by unitary. And then you can, using this unitary operator, you can apply it on the state, on the operator, and then it is designed in such a way that it preserves the expectation value of an operator on a state. This is because expectation value is something physical, but basis transformation is our human choice. You can choose different bases to define, to describe the same physics, so you shouldn't, your expectation value, which can be measured experimentally, shouldn't rely on the chosen basis. That's why expectation value is invariant under basis transformation. We also talk about matrix diagonalization. I think the rough idea is basically, although sometimes you see all these complicated matrices, you should always think in your mind that there is a nice basis choice such that I can bring this matrix to diagonal. If I represent this operator in its eigenbasis, then the operator looks like a diagonal matrix. And it's very convenient to work with diagonal matrix because if you perform matrix multiplication, you just need to multiply the diagonal matrix element with themselves, right? So element-wise, instead of doing the full matrix multiplication for generic matrix, which is terrible. Okay, so last time, towards the end, we talked about Hermitian generators. The intuition is like, because unitary operator, if we take a number, using an example of complex numbers, instead of thinking about complex matrices, unitary matrices are also complex matrices, but if it's a one-by-one unitary matrix, that basically is like this. A complex number, its Hermitian conjugate becomes the complex conjugate, and then if U dagger U equals 1, that means Z star Z equals 1. So in that case, we found that for complex number, if its norm is 1, then it must be a complex number on a unit circle in the complex plane. Each such kind of a number can always be represented as e to the I theta, which indicates a complex rotation, basically, in the complex plane. And theta is the amount of angle that you rotate. So, so if we now jump out of the number example and then go back to matrix, actually, every unitary matrix can be written as e to the I theta, and this theta hat is a Hermitian matrix. Hermitian matrix is like a real number, and unitary matrix is like a complex number with unit norm, and that's why it is called unitary. Although this formula looks very abstract, but I think it's always good to think that all these matrices, no matter U hat or theta hat, are represented in its eigenbasis. And that's very convenient, because if the Hermitian operator is represented in its eigenbasis, what it does is that it tries to target every eigenstate theta labeled by k. K is the index for the eigenstate. It targets that state and multiply that state by theta k, which is a real number, and then return the state. We know that if theta k is the eigenstate of this operator, right, then operator acting on the state basically rescale the state by a scaling factor, and the scaling factor is called the eigenvalue. And for Hermitian operator, the nice property is that the eigenvalues are all real numbers, so these theta k's are real numbers. Another way to think of that as a matrix is that if you are in the eigenbasis, then this basically is a diagonal matrix whose diagonal element is theta k from the first element to the last element, theta 1, theta 2, and so on. So, so basically, the Hermitian operator tells us how much real number should I multiply on a state. And that real number basically corresponds to how much angle I need to rotate in the unitary case. Once you raise this Hermitian operator to the exponent, it becomes a unitary operator. Hermitian operator is multiplying real numbers to the state, and unitary operator is multiplying a complex phase factor to the state. The complex phase factor is fully parameterized by the amount of angle you need to rotate. And the amount of angle, that piece of information is exactly encoded in Hermitian operator as the diagonal matrix element. So if you are in the diagonal form, everything becomes very simple. It's Hermitian operator is just diagonal of real numbers. Unitary is diagonal of phase factors, and they are simply related by the fact that the phase factor can be generated by real numbers, right? E to the I theta map, this exponential map. However, if you're not in the diagonal basis, things can be very magical. So for example, if you try to raise e to the I theta sigma y, and we know theta sigma y is not a diagonal matrix, and then you try to understand what the matrix looks like. It turns out to be a non-trivial matrix. It's not diagonal. But if you first transform everything into the diagonal basis of sigma y and perform this phase rotation and then transform it back, then you basically will get this result. Yeah. So all these non-trivial off-diagonal matrix element comes from the fact that you are not choosing the diagonal basis for the Hermitian operator to start with. But it's always, there's an underlying good choice of basis which correspond to the eigenbasis. And this eigenbasis is actually shared by both the Hermitian operator and the unitary operator. They share the same set of eigenbases. And then in that eigenbasis, unitary operator is like a diagonal of phase factors, and Hermitian operator basically characterize the amount of phase to rotate for every eigenstate individually. Okay, so given this close relation, we say that every Hermitian operator can generate a unitary transformation or unitary operator. And actually, the inverse is also true. And every unitary operator, there is an underlying Hermitian generator. That's the idea. So if U theta is a unitary operator that implements certain basis rotation by a real angle theta, and then if theta is small, we can basically try to extract the Hermitian generator by this small theta expansion. The idea is that if theta is small, we can say, okay, U hat theta. So this U theta, I should say, U theta looks like this. Okay, it looks like the matrix above. Okay, so what do I mean by this bracket theta? It means this is a function of theta. So this is a function of theta. But this function takes the real number theta as input, but its output is not a real number, unlike a real function. Its output is a matrix, which means every matrix element in principle can depend on theta, is a function of theta. So what do I mean by this U hat with a prime, with a first order derivative. That means I'm taking the derivative with respect to theta for every matrix element inside this matrix. And then that still forms a matrix, right? For example, cosine, if you take a prime, it becomes sine, and sine take a prime. I think cosine goes to minus sine, and sine goes to cosine, and something like that. So essentially, this is a new matrix which is given by the previous matrix while taking a derivative on every of its matrix element. So because Taylor expansion is a generic way to express a function with respect to theta by expanding over small thetas. So when theta is very small, you can Taylor expand cosine, you can Taylor expand sine, you can Taylor expand every matrix element in this matrix. And the expansion of every matrix element basically goes like U0, which means you basically take all the theta to 0, and then that's the leading term. And then you also take the first order derivative of every matrix element, and then substitute theta equals 0 to the matrix element. That gives you the coefficient of the first order term in delta theta. And like that, and so on, you can basically expand a matrix as a function of theta for small theta and like that. Why do I need to do this exercise? Because I want to tell you what happens there. This derivative is actually its Hermitian. It's related to its Hermitian generator. The reason, so first of all, one obvious thing is that U hat 0 is identity. If you take 0, it's identity. The reason is that this theta parameterizes the amount of angle to rotate. When theta equals 0, then there's no rotation being performed, so the operator is basically identity. But if you try to perform a small amount of rotation, then the operator will deviate from identity, and this U prime describe, the first order derivative describe what kind of deviation will happen in this matrix when you try to tune theta away from 0 a little bit from identity matrix. How much you deviate from identity matrix, okay? So this U prime operator is also a matrix, and then it is related to the Hermitian generator. You can rewrite it as U prime equals Ig, where G is the generator, is the Hermitian generator of this unitary operator. And then people also say that it generates infinitesimal rotation because this delta theta is supposed to be, when you perform Taylor expansion, your assumption in your mind is basically delta theta is very small, so it's like an infinitesimal rotation. It's like you try to probe if I go away from identity by infinitesimal amount of theta, how the matrix will change. And this change characterizes the generator. So the generator describes along which direction the unitary operator is going to rotate the vector, basically. And then if this U theta is unitary, you can show that its Taylor expansion, the first leading order term, sorry, this is not leading. The first order term, this is leading, and then this is subleading, but the first order subleading term is a Hermitian matrix. G, well, I'm saying G is a Hermitian matrix, and the whole thing is actually anti-Hermitian if you take also I into account. How to show that G is Hermitian? Well, you can start from the definition, because we define this U in the sense that it's unitary. So U is unitary, meaning that it satisfies this identity, right? So if U is expressed in this way with higher order term, which we don't care, and then U dagger will be expressed like that. And then also with higher order term, for now we don't care. And then you can just expand this two Taylor expansion, you will find that the first order term looks like this. In order for this equation to be identity at least, right? I'm not talking about higher order term. At least the first order term need to vanish. Of course, all the higher order term also need to vanish. But that's additional condition we don't want to consider for now. For now, at least the first order term vanishing, this already tells you that this G is Hermitian, because this term has to be 0, and then that's the definition of Hermiticity for G. So in this way, we see that if previously we just say, given every Hermitian operator, you can generate unitary. So, but now, today, we learn that given any unitary, you can use this idea of infinitesimal rotation to extract the Hermitian generator that is hidden behind the unitary transformation. And the Hermitian generator is simply the first order derivative of this unitary operator with respect to the rotation angle, and then there's a convention that's there's I times the generator is that first order derivative, basically, and then that a generator will be Hermitian. So if we know how to perform infinitesimal rotation, we can actually build large rotations by accumulating small rotations. For example, if I want to build a considerable amount of rotation, I can chop up this rotation angle theta. So I want to rotate by some degrees theta. Let's say theta is this much. And then I can chop it into small pieces. Every piece is only rotated by delta theta, but there are n pieces of them, such that n times delta theta is my large angle theta. Then I can think of it as either as a unitary transformation by the angle n times theta, or I can think of it as continuously doing this u of delta theta small angle rotation, but I do that n times. So, I should have this equality, and this equality basically shows us that if the infinitesimal rotation is given by this expression, then do it n times is like nth power of this matrix. Be aware that this is a matrix because G is a matrix, I is a matrix, and 1 is a matrix, right? So everything is a matrix. So when the theta is small, then basically you can try to show that this expression goes to the exponential map. I'm trying to derive this exponential map for you here. So how to do that? Basically, you can take a log on both sides. So log is also an operator function. It's not taking log for every matrix element. It's the function level kind of logarithm. But if you do that, that basically becomes n times log of this one. But log of this one has a basically Taylor expansion again. So the leading order term is like that. So to the leading order, to the delta theta order, basically we can show that U is related to G in this way. But n times delta theta basically gives you the finite angle rotation. So this shows that this G that we extracted by taking first order derivative of the unitary is indeed the Hermitian generator that generates the unitary. Because if I use this infinitesimal rotation kind of idea and do it n times, I really reconstruct the finite angle rotation from that. So, all this discussion is trying to show a fact that every Hermitian operator, which previously I wrote as theta, but here I wrote as G, but there's no big difference. G is called the generator, and theta, well, is the theta angle times G, basically, in this expression. Because previously we say everything above the exponent is like a Hermitian operator. But actually, I can also factor out the amount of angle that I want to rotate. And what is essential there is actually this generator G. And then you can actually extract this generator, regardless of the rotation angle theta, from the unitary operator. Okay, so every Hermitian operator generates a unitary, and every unitary operator is generated by a Hermitian operator. That's the idea. That's a very close relation between them. Any questions? Yes?
Why does the ln go away?
Why does the ln go away in the second step? Because ln has a very nice property that log 1 plus x, there's a Taylor expansion for this x. And then that goes like x plus other subleading terms, okay? If you don't believe. I actually forgot about this Taylor theory, but I can do it right now. 1 plus x, and then x, that's expand to the fifth order. So there's a Taylor theory expansion for log 1 plus x, and the leading order is like x, okay? Any further questions? Okay. Okay, so So if that's, so I'm going to talk about, continue really about time evolution now, because we have enough preparation about unitary and Hermitian operator and their relations, which is very important. So the first thing I want to prove is that in quantum mechanics, time evolution is unitary. Why we want to talk about unitary operator is because time evolution is unitary. What does that mean? Well, that's actually a very fundamental assumption. Unitarity basically implies that the information is never lost in the quantum dynamics. There's a basic assumption about quantum dynamics, that is the quantum information is preserved under quantum dynamics. That means if you have two identical and isolated systems, that means if you have a evolution process, you do it here and you do it there, you build two identical systems and then isolate them and then do the experiment under the same condition. Then if you start from different initial states, or like distinct initial states, then this difference will remain. So different state will, after time evolution, still remain different because their initial condition is different, but the unitary, the time dynamics is the time dynamics is supposed to be identical because I'm using like an identical copy of two systems to evolve the same state, to evolve the states, right? So if the dynamics is the same, then different states evolve to different states. And this difference is towards both future and past, meaning that if you start from different states, in the future they will be different. And also in the past, they are also different. If you evolve backwards in time, it's both directions. Why do we need this? This is because if different states evolve into the same state, you are losing information. Because originally, you can distinguish the states. They are different, meaning that you have some measure. For example, they correspond to certain observable, taking different observation value. But if they evolve into the same state, that means in the future, you cannot distinguish this piece of information. You cannot know what's the difference between the initial states. So you are forgetting about information. And that is in contradiction with the assumption. That is an assumption. We don't know why our universe is like that, but it seems to be true that quantum information is never lost under time evolution. And also, if you start out from the same state, identical state, they will follow identical evolution, both towards future and the past. I think it's a similar statement with the previous one, like different state cannot evolve into the same state, and the same host, like same state, cannot evolve into different state as well, both in the future, towards future and towards past. If the same state evolve into different state, that means you need to add information into the system in order to distinguish them, right? The same state, the fact that it can be evolved into different state, meaning that you have something that you don't know about the state. It seems that the state is the same at the beginning. It's secretly actually different, maybe. So if you really know that the state is identical, then they should follow the identical evolution. So it is such a simple principle that information is never lost or never being added. If information is conserved, basically, under the unitary dynamics, under the time evolution, it's sufficient to prove that the time evolution is unitary. So if you assume time evolution has this property, okay, another thing I want to say is that the measurement actually does not satisfy this condition. Because under measurement, you have some non-deterministic process. It's all stochastic, and then based on probability distribution, you pick a state. So measurement is basically out of the discussion of time evolution. When we talk about time evolution, we talk about the deterministic evolution of the system. But why the underlying quantum system is always governed by this unitary deterministic information preserving evolution, but when we measure the system, it seems that it becomes non-deterministic. This is still an open question in the frontier of physics. People believe that it has to do with the fact that it's a quantum many-body system and we cannot keep track of all the information. So it is basically limited by humans' ability to process information that unfortunately we we can't perceive all the information, that there seems to be an information loss. So at the fundamental level, people still believe during even the measurement process, the whole quantum system as a whole is still information preserving. It's just we cannot read out all the pieces of information in the many-body system. Yeah, so that's the current understanding. But anyway, we're not going to touch upon that. I'm just going to talk about evolution of quantum state under this time dynamics, and then it is supposed to be the same state remains the same, and the different state becomes different. So that means if you start from the initial state, then you will evolve into a final state. And the fact that it is deterministic, meaning that there is a formula that can tell you if you start from the initial state, which final state you should reach. And then this formula looks like this. You start from this cat state, you use an operator to operate on this cat state. The operator will change the state and deform it into a new state. And that operator is called the time evolution operator. So if you start from the initial state at time 0 and evolve into time t, then the unitary operator is also labeled by the amount of time. This u of t, basically this t time here, labels how long in terms of time you want to evolve the state. Okay? So we can show that this u of t, the time evolution operator, is a unitary operator because of the following two properties. The first property is that the distinct states must remain distinct. So what do we mean by distinct state? Suppose we have two initial states. One is called theta, the other is called phi. The fact that they are distinct, meaning that their scalar product is 0. So that's the definition of two states being distinct, as we studied previously. Because if you are on this state, there's no probability to observe the system in the other state, so you can distinguish them. And then the distinct state remain distinct, meaning that in terms of the final state, the inner product or scalar product must also be 0. But the final state is related to the initial state by unitary evolution. For the cat, it's u times psi. For the bra, it is u dagger times psi. So this means that this expression must be 0 for any phi and psi that are orthogonal to each other. So that's one fact we need to keep in mind. Another fact is that if you start from the identical state, then I just use the same symbol, psi 0 and psi 0. They are identical, and suppose they can be normalized, then the identical state has a scalar product of 1, then after the time evolution, it still remains identical, meaning that their scalar product is still 1. And then that's the idea. And then they are still identical, still has the 100% of overlap between them. So now, because this principle, this is a very general principle of this u dagger or u of t, the time evolution operator. So instead of treating phi and theta as some arbitrary states, you can actually think of them as members of any orthonormal basis. Because if you start from an orthonormal basis, all the states, different states are all distinct, right? And then the same state is also normalized. So starting from an orthonormal basis like I and j. So I and j, if you treat them as initial states under the time evolution, they satisfy this condition that without this unitary in between I and j, the scalar product between them is already delta ij, right? So that satisfies these two conditions. Now with this unitary, because these two conditions leads to these two conditions, well, after the unitary evolution, the states still remain orthonormal. So that means this expression must hold. But what is this expression? If you take a look at this u dagger and u and treat them as this is still an operator, right? And treat them as a matrix. This I and j, scalar product with I and j, basically extract the matrix element of the matrix of u dagger and u. U dagger and u is a matrix. Its matrix element in the ith row and j's column is delta ij. But we know delta ij is this chronic delta symbol, which means that only I equals j is 1, and when I doesn't equal j is 0. So there's only one matrix that satisfies this property, that is the identity matrix. So we know that if this matrix element of this operator looks like a matrix element of identity matrix, then that basically means that this operator is identity operator, basically. So that shows that u dagger u is identity. But U dagger U is identity is nothing but the defining algebraic property of unitary. So that proves that this time evolution operator is unitary. Yes, questions?
If like two states started out, like rather than their overlap being 0, if it started out as like being like 0.5, would it still be 0.5 after some time evolution?
Yeah. Yes and no. Let me see. Yeah, maybe yes, because yes, if U and U is annihilate with each other as identity, so whatever 0.5 here will be inherited after the time evolution. That's right. Yeah. Okay, so the reason I don't talk about this 0.5 case because for the purpose of this proof, it's sufficient to discuss this extreme cases of distinct state and identical state, but the statement is also true for any finite overlapping states. Okay, so all this discussion is trying to show us that starting from the very general principle that, or the assumption that in quantum dynamics, information is never lost or increased, it's preserved, just from this very simple principle, you can derive that time evolution must be unitary. Time evolution must be such that you apply, it's like you apply a unitary operator on a cat state. But we have just learned that every unitary, there's a Hermitian operator behind, right? That Hermitian operator encodes the amount of transformation you need to perform under this unitary. So, so there must be a Hermitian operator that generates the time evolution unitary. And the Hermitian operator that generates this time evolution unitary has a name. The name is called Hamiltonian. So previously, maybe when you learn quantum mechanics, maybe professor says that Hamiltonian is the operator that corresponds to energy. Yeah, that's true. But Hamiltonian, its definition in quantum mechanics actually is defined to be the generator of time evolution. And it turns out that energy is the generator of time evolution. It's just, you can think of it the other way around. It's like a definition of energy. What do we mean by energy? Energy is defined to be the generator of time evolution. So as a unitary operator, the time revolution operator is also generated by a Hermitian operator called Hamiltonian, and Hamiltonian can be extracted from the unitary operator by using this time derivative trick we just mentioned above. You start from the unitary evolution and consider infinitesimal evolution, and then infinitesimal evolution is described by the first order time derivative of this unitary operator and take the value at t equals 0, and that basically defines or gives you the Hamiltonian. So for a small delta t, infinitesimal evolution looks like this. And then therefore, for small delta t, the state will evolve in such a way. So if you start from a state at time 0, apply this infinitesimal unitary operator, it basically applies the whole bunch of operator to the state. But the first term, so the whole operator acting on the state. But you can split it, right? The first operator acting on it minus the following operator acting on the same state. The first is an identity operator, so it's doing nothing. The states remain the same. All the change of the state coming from the second term, where the second term, when there is a Hamiltonian acting on the state, remember that the Hamiltonian, by definition, is Hermitian because it's a generator of unitary. Generator of unitary is always Hermitian. Okay, so given that equation, you can basically move this delta 0 to the other side. So that tells you so not delta 0, I mean psi 0. Move psi 0 to the other side. That gives you an expression of psi delta t minus psi 0. So this is the difference between the time evolved state by an infinitesimal amount of delta t and the original state before the evolution. Because the change is very small, so you don't want to describe the change itself. Instead, you want to describe the change per unit of time. So you want to take the difference and then divide it by the infinitesimal amount of time that you evolve. So this basically, you can rewrite it as a time derivative of the state. And then on the other hand side, if you start from this equation, you can show that what happens on the other side is basically the Hamiltonian operator acting on the state as a matrix multiplying the state vector. So this is, so this derivation, in this derivation, there is really nothing special about t equals 0. Although in this derivation, we start from time equals 0 and then try to see with an infinitesimal time evolution what happens. But you can start from any time t and then do the same exercise. You will reach the same formula. The only difference is that this psi 0 should be replaced by psi t. So we arrive at the differential equation that tells us how the state vector as a function of time should evolve, basically given its first order derivative, how it should evolve with respect to time. Because if you want to evolve the state, what you need to do is you apply the Hamiltonian on the state and calculate the derivative. The derivative is like the idea of velocity, right? If you want to evolve the coordinate of a particle, basically you compute the velocity. Velocity is the time derivative of coordinate with coordinate derivative with respect to time. So that's the velocity. Once you know the velocity, you can go one step forward in the direction of velocity and following the magnitude of the velocity, and then you know how this coordinate will change. The same thing happens here, although this psi as a state vector is no longer a coordinate of a particle, but it is still a vector in a high-dimensional Hilbert space. So it's still a bunch of numbers. As long as you know what is the velocity of every component of this vector, right, you know how to evolve this vector in time because you just need to calculate this velocity by applying the Hamiltonian matrix on the state and then evolve it forward by an infinitesimal amount. And now you have a new vector, you continue to apply Hamiltonian on a new vector and calculate what's the new direction of the so-called velocity, which is the left-hand side of the equation. And then you can continue step forward by an infinitesimal amount of step in time. So by accumulating all these infinitesimal time evolution, you can really evolve the state forward in time by a finite amount. And this is the principle of Schrödinger equation. This equation just is the Schrödinger equation. It has the name. Schrödinger proposed that. So it is the quantum motion equation of motion. It's an equation of motion of quantum state. And in many cases, this Hamiltonian itself, so in general, Hamiltonian can be time dependent because we say that Hamiltonian is nothing but the unitary time evolution operator's first order derivative. So unitary operator is a function of time. It's a matrix function of time, meaning that given a time, it gives you a matrix. So the matrix, every matrix element in this unitary operator is a function of time. So if you take the first order derivative, you should still expect that every matrix element in this matrix still a function of time in general, right? If you have a function, take a first order derivative, it's still a non-trivial function. So in general, Hamiltonian operator is a function of time because unitary operator can depend on time very arbitrarily. So in general, it can be time dependent. For example, it can describe the process that, for example, if you shine the light on an electron, then light is like there's an oscillating electromagnetic field. So the electron will experience an E field in this direction, and then after a second, it goes like that direction. So you will see the environment keep changing. So if a particle is, a quantum particle is living in such a keep changing environment, it basically experiences a time evolution which has a time-dependent Hamiltonian. But in many cases, we consider this Hamiltonian to be time-independent. That's also very often, if you just put a particle in a uniform electric field without changing anything in time, then it's a time-independent problem. And in many cases, we encounter this kind of problem because if we assume time translation symmetry, that means the system has a translation symmetry in time. The system or the environment the particle experienced doesn't depend on time, then the Hamiltonian also doesn't depend on time. So this Schrödinger equation has two versions. One is the time-dependent Schrödinger equation. The other is time-independent Schrödinger equation. And if you open up your textbooks and see what Schrödinger equation looks like, what you will find is that there is an additional factor, h bar, in the front. So what happened to the Planck constant? I'm deliberately missing that. So in quantum mechanics, actually, if you want to balance this dimension, you actually need to add this constant. So the observable associated with Hamiltonian is energy in order to balance the dimensionality, because this side is energy, on that side is 1 over time. So 1 over time doesn't equal to energy, right? 1 over time times the Planck constant has the same same dimensionality as energy. So that's why people introduce this Planck constant just as a factor. This Planck constant is introduced. It is all because that energy is measured in joules, and then time is measured in seconds. These two units was invented before quantum mechanics, very unfortunately, so we have to stick to them. So there has to be a conversion unit, conversion coefficient in order to convert joules to 1/2, right? So if quantum mechanics was first invented, maybe people won't create a new unit for joules, just use second. You can define energy already. And in that case, Planck constant will be 1. So why Planck constant is so small? You can see this is a very small number, 10 to the minus 34 joules second. Well, the answer is more to do with biology than physics. It's actually a question about why we are so big, so heavy, and so slow. Because when humans define these two units, joules and seconds, it's based on the human experience. Second is something we can experience in our daily life. What is 1 second evolution in time, right? And joules is an energy unit. Also, we can operate. It's we often can do it in the lab, right? At a macroscopic level. So joules and seconds are natural units that describe macroscopic physics that happens surrounding us. And we are biological systems, and then it's unfortunate that we are so big, heavy, and slow that the Planck constant seems to be so small, because a natural choice of quantum mechanics will be setting Planck constant to 1. And it is actually also a common practice in theoretical physics, in particular particle physics. Or condensed matter is also the same thing. When we want to deal with quantum mechanics, it's always very convenient to set Planck constant to 1. But it's unfortunate due to historical reasons that there's a constant there. So like in your homework or exam, if you want to set Planck constant to 1, you are welcome to do that, no problem with that. So either this version, a more precise version, you can call it Schrödinger equation, or the previous version without the Planck constant is also fine. It's basically the same thing. Okay, so that's what I want to talk about Schrödinger equation. And maybe in the last 9 minutes, I can briefly mention, I can summarize things. So this comes to the final postulate number 4 of quantum mechanics. It's about dynamics. Let me remind you that postulate number 1 is saying that every state in the quantum system is described by a ket vector. Postulate number 2 is saying that every observable is described by a Hermitian matrix. And then postulate number 3 is about measurement. It says that when you do the measurement, you only observe the eigenvalues of these Hermitian operators, and then the state will collapse to an eigenstate after the measurement, given by whatever, depending on what measurement outcome you obtained as an eigenvalue that specifies the eigenstate. So the first 3 postulate talks about states, observable, and measurement. And the first one is about dynamics. It's about how system will evolve in time, how the state will evolve in time. So again, states still described by a vector, and the time evolution of the state of a quantum system is described or governed by another Hermitian operator, and then that Hermitian operator is called the Hamiltonian of the system, and then the evolution happens according to the time-dependent Schrödinger equation, which is written down there. Okay, so that's the final principle. So with all these 4 principles, we can basically, first of all, quantum mechanics provide the description power. It describes the states as vectors, and it also provides the prediction power. It predicts how the states will evolve in time. It also predicts after the time evolution, if I want to make a measurement, what will I see? And then it also tells you, after I see that, after the measurement, what the state will collapse to. And then you can further apply time evolution on that collapsed state and evolve it forward, and then predict what will be the future of the state. So you can just continue using the dynamics and the measurement postulate number 3 and number 4, which correspond to 2 fundamental processes in quantum mechanics, measurement and time evolution. That's the 2 things I want to talk about. So if the Hamiltonian is time independent, so this is the generic case where Hamiltonian is time dependent, but I didn't write it down explicitly there, so I should really put a bracket here, Hamiltonian is time dependent. But if Hamiltonian is time independent, this equation can be simplified because we can first find its eigenvalues and eigenvectors. Hamiltonian is time independent, meaning that it's a definite Hermitian matrix that will not change in time. So we really has only one Hermitian matrix in our hand. And then with that Hermitian matrix, we can try to do a spectral decomposition by finding its eigenstates and eigenvalues. And this equation, solving this eigenequation, is also sometimes called time-independent Schrödinger equation. Because in the time-independent case, you don't really need to solve this differential equation in time. You only need to know what's the eigenstate and eigenvalue. Why? Because once you know what are the eigenvalues, whatever time evolution will look like that. Well, basically, every eigenstate, every generic state of the quantum system will simply be a linear superposition of these eigenstates, right? So as long as we know how the eigenstate evolve in time, we know how any state evolve in time. So the eigenstate will evolve in time in this way. This is because the eigenstate is eigen in the, under the action of Hamiltonian, meaning that Hamiltonian only rescale this eigenstate by a real factor. But we know that the time evolution unitary is a unitary generated by this Hermitian operator, by this Hamiltonian, and it is generated in such a way that it basically raises this energy to the exponential factor. Of course, there's other things like Planck constant and time. You can take care of them following this equation. So you can show that what happens when you apply the unitary operator on this eigenstate is just to rotate this eigenstate by a phase factor. And then that's all you need to know. So in general, if you have a generic state, and then now you can predict what is the generic state evolving on original state, basically, you need to go and decompose everything in the eigenbasis. This term, this scalar product describe the superposition coefficient of this initial state on the eigenbasis, energy eigenbasis, because this eigenbasis are eigenbasis of Hamiltonian, so people also call it energy eigenbasis. So for every initial state, you can decompose it, and for every energy eigenstate, it evolves under time and following this phase rotation idea. So eventually, this is the when you combine everything together. So this will be a number. This will be a complex number which does not depend on time. All the time dependence come from this exponential factor. But this exponential factor and this complex number together, anyway, it's just a time-dependent complex number. So you are using this complex number to combine all these energy eigenstates and summing over all the state label I, basically. So that will be a new state. And that state will depend on time. And that basically describes the time dependence of your state. So as long as you know what are the eigenstates, you can always use the spectral decomposition or change the representation to the energy eigenbasis. And you use this idea to do time evolution. Another way of writing this, because this, the whole operator in the front here can simply be written as a unitary operator, as we mentioned above. So as we said, that time-independent Hamiltonian generates time evolution unitary via the so-called matrix exponentiation. This is the matrix exponentiation. It's not element-wise. It's on the matrix level. But so-called on the matrix level just means that if you are in the energy eigenbasis, what happens is you raise the diagonal matrix element of the Hamiltonian, because Hamiltonian in its own eigenbasis will be diagonal. You just raise every component to the exponential like that. Okay, so that's the idea. However, for time-dependent Hamiltonian, there's no such a clean formula that you can immediately write down what this u of t should be. So what you really need to do is to do the evolution, carry out the evolution step by step, meaning that you need to use an infinitesimal time times the Hamiltonian to evolve the system forward by an infinitesimal step. And then you need to accumulate all steps together, meaning that you need to multiply all the time evolution, small time evolution together. But multiplying an exponential function together is like summing the exponential summing on the exponents, right? So people sometimes also write it as integration of time from 0 to t, and then I don't want to go into too much detail of this expression. This is if you can understand, you can understand. Otherwise, don't worry about that. So I'm just showing that there is no simple formula for time-dependent Hamiltonian evolution. But all we want to learn is that for all the homework and exam about time-independent Hamiltonian, we never touch that. So, so for time-independent evolution, it's given by the matrix exponential. So it's very important that you know how to do matrix exponential, and then many of the problems will be about, given the Hamiltonian, try to write down the time evolution operator acting on the state and predict something, right? So you need to be very familiar with this exponentiation. So with that, thank you for your attention. Yeah.